Hello, everybody. Good afternoon. Good morning to some of you, and also good night. So it's a pleasure to have here today another IEEE Sequencing System Society Rio Grande do Sul chapter talks. So generating from Brazil to all around the world with very excellent speakers like we are going to have today with Professor David Pan. So David Pan has a very brilliant CV. We don't have time here to read all his achievements because it's going to take too much time, but just some few ones. So David Pan is currently in, it was not updated in this slide, sorry. David Pan, the professor in the Department of Electrical and Computer Engineering, the University of Texas at Austin. So his research interests include the bidirectional AI and IC interactions, electronic design automation, design for manufacturing, hardware security, and CAD for analog mixed signal ICs and emerging technology. He has published over 380 referred journals, conference papers, and he has 8 USA patents. He has served in many journal editorial boards and conference committees, including various leadership roles such as ICCAD 2019 General Chair, ISPDAC 2017 TPC Chair, and ISPD 2008 General Chair. He has received a large amount of awards, include SRC Technical Excellence Award, 19 Best Paper Awards, so this is a very impressive achievement. DAC Top 10 Authors Awards in 5th decade, ASP-DAC Frequently Cited Author Award, Communications of ACM Research Highlights, ACM CDA Outstanding New Faculty Award, NSF Career Award, IBM Faculty Award 4 times, and many international CAD contest awards. He has graduated 36 PhD students and postdocs who have won many awards, including the first place of ACM Student Research Competition Grand Finals in 2018, ACM CDA Student Research Competition Gold Medal twice, ACM Outstanding PhD Dissertation in EDA Award twice also, ADAA Outstanding Dissertation Award twice also, and he is a fellow of IEEE and SCPIE. So, David Pan, thank you very much to accept our invitation. It's a pleasure to have you in our set of CASS talks. And then I give the control to you to do your screen sharing to start your presentation. Thank you very much.
Okay, first of all, thank you very much, Ricardo, for your very kind invitation, and really impressive to see such a large amount of activities in Brazil, led by your chapter. So it is also my great pleasure to share with you some of our recent results. Let me try to share my screen. Can you see my screen?
It's coming. Okay, perfect.
Good. All right, so hello everyone. Good morning, good evening, good afternoon, depending on where you are. So today I'm going to talk about AI for IC and IC for AI, essentially also the closed loop perspective between these two, and also share with you some recent results from my research group. So as we all know, AI has been, really have a huge booming recently. And the reason behind the AI booming really lies down the ABC behind. A stands for the algorithms, such as CNN, RNN, GAN, etc. But meanwhile, B, we do need to have a huge amount of data to make these algorithms work very well, because these algorithms, need to have, especially those deep learning, the network is huge, need a lot of data to fit it. And meanwhile, such a huge amount of data, meanwhile with a very complicated network, so do need to have huge computational power. So that's why I see the chips, which is underlying all these chips, fuel such kind of powerful computations, no matter whether it's more powerful CPU or GPU, and ASIC, which is dedicated for AI accelerations, or FPGA, right? So there are tremendous efforts here. So if we talk about IC design and manufacturing, in particular nowadays we are talking about nanometer regions, right? Like 7 nanometer, 5 nanometer, or even 3 nanometer, as TSMC is announcing their future fabs, right? So the complexity for both design and manufacturing are huge. For example, this is a SoC from NVIDIA. It has almost 10 billion transistors. To design such a large SoC, usually we have to divide and conquer. So for example, you will divide them into 1 to 2 million cells per partition, and then run sophisticated design closures to reach timing and the power closure. But such processes take long time, because even such a partition for 1 to 2 million cells to reach a back-end design closure, it could take several days. All right. Then what you see at the design, basically after you finish your design, right, you will have a bunch of polygons, and at different layers, this is so-called masks, right? And this kind of mask, when you send to the fab, they need to be fabricated layer by layer, right? However, when your feature size and spacings are very, very small, you may have distortion at the fab, and you may have to do a lot of so-called optical proximity correction or other mask synthesis to make sure it is kind of as close to as what you intend to print and still function well with good yield. So this is really like a miracle when you're talking about billions of tens of billions of transistors and wires, right? So as you can imagine, design process is really complicated. Here is just some very high-level view for the modern IC design and manufacturing. Usually you start from some system-level specification, architectural design, functional design, and logic synthesis. Then you go through physical design, and then you will do mask synthesis, verification, and then finally you fabricate it, and then you do package and testing, right? So even for physical design, it actually has many, many steps, such as floor planning, placement, clock tree synthesis, routing, and so on and so forth. And then for mask synthesis and verification, to ensure what you design can be fabricated with good yield, you may have to do test pattern generation, tune your list of modeling, and use that to guide all kinds of mask optimization, such as OPC, optical proximity correction, SRF insertion, and so on and so forth, right? So then, once you send to the fab, if it doesn't work, you have to go back to the previous stage, maybe to fix some mask issues or fix some physical design layout and so on and so forth. And if you cannot meet your timing or power, you may have to even go upper level to fix some architecture designs, right? So as you can see, these kind of modern designs have tremendous amount of challenge to meet all these power, performance, area constraints, and manufacturability, yield issues, reliability, security, and last but not least, design cost, right? So as you can see, this is a slide from DARPA a couple of years ago. As you can see, this red line basically shows the design cost, right? Total hardware design cost involved hardware cost, but the biggest portion here, as you can see, is the design cost. So this is certainly not acceptable. So that's why 2 years ago, DARPA started the ERI initiative. And under that, there's an IDEA program and POSH. The goal is to have a next generation hardware compiler to help reduce such design cost. So the DARPA grant challenge and the vision is that hopefully we can have some no human in the loop, 24-hour turnaround time to reach this kind of design closure. So how can we do that? So certainly, we are looking at the new AI capabilities that the AI hardwares and softwares can provide. But then the question is how, right? So, in the my research group, right, we have been looking at closely these two aspects. One is AI for IC, another is IC for AI. So when I say AI for IC, essentially how we can leverage AI hardware and software to enable agile and intelligent IC designs. So equivalently, we can achieve, Moore's law's, kind of benefit, right? And so that, without really using the really most advanced technology nodes, right? So because nowadays, right, so we know that there are just too many transistors that are really not optimized during the design stage, right? When you have billions of transistors, right? So a lot of them are, really used suboptimally. When I say IC for design, of course, you already see there are a lot of, even commercial products for customized ICs and AI accelerators. So the really question is that how we can achieve better energy efficiency. And a lot of these machine learnings, right, so they indeed consume a huge amount of power. For example, GPT-3 recently just released, like the training cost could be, many $1 million, right? So interestingly, I think the IC and AI indeed has some similarity in terms of this kind of exponential trend. So this yellow line shows the Moore's law. Essentially, the number of transistors will double every 18 months or something like that, right? But if you look at the number of machine learning papers which people have posted in archive in the last 10 years or so, it actually beat Moore's law to a certain extent. Okay, so it will be very interesting for these two laws, kind of exponential, for the IC Moore's law and this exponential machine learning, mostly AI, software algorithm related papers to work together. So that will be really interesting. So in the next, basically, I will talk about our recent efforts on some of these two aspects on AI for IC and IC for AI. So first, how AI can help IC, right? So the machine learning actually can be used as some kind of hammers to tackle each of those steps, right? As I mentioned, right, IC design has a lot of complicated steps. Here, I just show some key steps in physical design. And for example, placement, routing, mask synthesis, and verification. So inside each of these, you can use machine learning to build better, algorithms for each of these steps. And meanwhile, you can use machine learning to build a bridge between these steps so that you can connect these steps together, as I showed in the previous slides, right? Because indeed, right, so you may need to do some back annotation and stuff like that. So at the early stage, for example, during placement, we can kind of predict the downstream effect so that my placement is more aware of routing or even more aware of the manufacturability. That will actually get your design closure design manufacturing closure much faster. So in the following, I will show you some case studies we have been doing. So how we can actually use machine learning to help IC design. So the first case study is on a DreamPlace. It stands for Deep Learning Toolkit-Enabled GPU Acceleration for Modern VLSI Placement. This is a paper my group published in collaboration with NVIDIA. And last year, we got a Best Paper Award from DAC. We also made the source code available in the GitHub. So as we all know, right, placement is one of the center stages in modern IC design, because only when you have placement, you have interconnects, right? You know how long your wire is, and so on and so forth. So it is really, really important because in nanometer designs, right, your interconnect delay actually dominates your transistor delay, right? However, placement problem is a classical problem, and it has been shown that is an NP-hard problem. And not only that, in modern designs, we have to deal with many, many million cells, right? So we care about quality. We also care about the runtime. So as placement is a classical EDA problem, you can date back to 1970s or even earlier, right? Whenever people start to design ICs, they have to figure out where to place their blocks, where to place their standard cells, right? So early days, people used partitioning or simulated annealing type of algorithms. But recently, the more trend is to use more analytical techniques. And again, there are many, many placement papers. Here is just a very small subset of some representative techniques. But to make the story short, right, the current state of the art placement is using, especially global placement, is to use some kind of analytical technique, try to formulate it into a nonlinear optimization problem. let me show you how a typical state-of-the-art nonlinear placement algorithm looks like. Right. So your goal is to minimize total wire length. All right. This WL is a wire length. The wire length, of course, is a function of XY location of your the cells, and meanwhile there's a netlist connections between them, right? But if you just want to minimize wire length, it's not very meaningful because you could just have cells on top of each other, then the wire length is 0, but that's not interesting. So we still want to spread the cells, in particular during the global placement, which is the most important step in placement. So usually you can actually relax this problem to unconstrained optimization problem. This lambda is something called a Lagrangian multiplier. So essentially, if you find that your density violates this, if your density is too high, you put some penalty here, right? But as you can see, this entire optimization process takes a lot of iterations to get high quality results. So that's why usually to get a state-of-the-art placement results, it's a huge development effort. And the runtime also can be quite large. It's easily take hours, right, to get a good placement for million-plus cells. So then you may ask, hey, what is a DreamPlace? So a dream placement engine is that, first of all, we would like to have the best quality of results, whether it's congestion or timing or power. By the way, wire length objective function that I just showed here, this is a very fundamental metrics for placement. So later on, if you say, hey, I care about timing, and you can actually put some weight in front of your wire length. If it is a timing critical wire length, you give it a higher weight, right? So again, right, essentially you can easily just recast it using this basic formulation to solving timing problem or power or congestion. But as you can see, during the timing closure or design closure, so you need to run this kind of placement probably many times. So that's why speed is very, very important. And we also hope to have a low development effort to develop a state-of-the-art placement engine. For example, let's say originally when we for example, when we talked to UC San Diego RePlace team, right, it took them like 1 year to develop that, right? And we say, hey, can we, maybe, take a month or something, right, too. So also we would like to have the placement engine to be extensible. So let's say next time I got some new algorithms or new acceleration techniques or new like a GPU architecture. So you don't want to restart from scratch, right? Your placement engine to be really easily extensible, right? So that's why you got to dream big, right? If you want to do high impact kind of breakthrough kind of results. So yeah, our dream here is to have a 10 million cell design placement in high quality in finish in minutes, right? So our motivation actually comes from the recent advancement in deep learning hardware as well as software. In terms of hardware, we know that the GPU nowadays really in terms of, in particular, in terms of training, neural network training and inference, those areas, right, for deep learning, they really have tremendous amount of speed ups compared with their CPU counterpart. And by the way, yeah, so the largest GPU company, NVIDIA, I think the market value now is bigger than Intel, right? So then in terms of the toolkit for deep learning, the developers are huge, right? Because of thanks for the open source community like PyTorch from Facebook and TensorFlow from Google, right, etc. So they do have a lot of really highly optimized and mature software kit there that we could leverage. So our DreamPlace strategy is to propose a novel analogy by casting the nonlinear placement optimization into a neural network training problem. So then we can greatly leverage this deep learning hardware as well as software toolkits and enable very, very high parallelisms and acceleration while getting state-of-the-art results. All right. So let me show you how to do such analogy. So when we do like a deep neural network training, right? So usually you have some data instance. Oops. So you have some data instance. So for example, this is some image, and then you have a label, whether it's a dog or cat or something like that, right? You go through the neural network, and then you have some error function. You will compute the error function, and then you will do some backward propagation. This weight is the trend value that you want to train your neural network, and you can compute the weight with respect to your weight, and then you do backward propagation and then forward propagation, through multiple times. At the end, you can minimize your error function. Then after trend, so you give me a new image, I can directly tell you, whether this is a dog or a cat, right? So to avoid the overfitting or something like that, so people usually also introduce some regularization factors. So not only you want to minimize the error function, but you also want to have this regularization to control overfitting. So meanwhile, if you look at actually our placement objective, right? We want to minimize wire length subject to certain density constraint, right? We don't want your density at any location to be too big, right? So interestingly, we can also cast this into a neural network kind of analogy problem. So our instance are net, right? And our target, you want to minimize wire length. So we set our target to be 0. So any error function is going to be the final wire length. And the wire length, is a function of XY location. So that's why the weight here is indeed each cell's XY location. All right. So again, we can do forward propagation to compute wire length, and meanwhile backward propagation to compute the gradient of wire length with respect to the XY location, right? Which is the W here. And meanwhile, of course, we can also throw in our density function there so that we don't do overfitting. So I won't go into all the details, but as you can see, this is a beautiful analogy. So then, to develop a new placer, our DreamPlace, actually we leveraged a lot of this mature and highly optimized deep learning toolkit, which already available in the Python or in the CUDA library, stuff like that. And so there are a lot of nonlinear optimizers there, and automatic gradient computation, and so on and so forth, ReLU. So what we need to do is to plug in some placement API. And meanwhile, of course, we still need to have our customized operator for wire length computation and density computation. So by the way, to match the results with the previous state-of-the-art academic placer for placement, replace, we actually matched, we also implemented this Nesterov's method, which is a nonlinear optimizer. But actually, later on, we also used like Adams and other stochastic gradient computation. So we got some similar results, right? So in terms of the wire length computation, this is a wire length formula. It's a kind of nonlinear function. It's to smooth the half-parameter wire length. Again, I won't go into details here. And we also have different schemes, right, related with how we can accelerate it. So whether we accelerate it through one thread for each pin or one thread for each net to do massive parallelism. But anyway, we found that for each pin to do this kind of thread assignment is faster. And in terms of the density computation, so this is, again, the same paper algorithm from the ePlace and the replace. Essentially, you can model each cell as a particle. And essentially, because you have some kind of electronic charge, if your density is very high, it will automatically push the cells to be away, right? So it can be governed by some Poisson's equation. Again, I won't go into details, but the bottom line is that to solve it, when you are trying to compute the density and also compute the density gradients, so you can use some customized discrete cosine transformation, DCT, and also inverse DCT to compute it. And it turns out that we can also leverage highly optimized FFT kernels in deep learning toolkit. So instead of reinvent all these wheels, right? We can use that. And also we have developed some kind of customized kernels, and compare with the native DCT kernel in TensorFlow, we found that we can actually get a 1.4x speed up. So Then we actually compared our DreamPlace with the previous state-of-the-art RePlace, which actually runs on 24-core Intel CPU. And we only have one CPU to read the design, and the rest computation for the global placement is only one NVIDIA GPU. So we can, since we matched the algorithms, so we can get the same quality of results. But in terms of the runtime, using DreamPlace, it is actually 30 to 40x faster compared with RePlace. In terms of the largest design of the 10 million cells, that is a design from NVIDIA, our collaborator for this project. We found that in 10 million cells, it only takes 5 minutes for the entire global placement and detail placement. Actually, in our recent version, which we also have acceleration for detail placement, so we can finish the entire thing within 1 minute, right? Because once you do such an acceleration, the bottleneck becomes original bottleneck is global placement. Now the bottleneck is detail placement. But now we also accelerated that detail placement, so now it's actually everything works within 1 minute, right? Instead of several hours. So here is just some animation, shows you, how the process works. But the bottom line, as you can see here, right, our GPU utilization is very, very high, close to 100%. And so in terms of the dreams we had at the beginning, right, so we want to have the best quality, we want to have ultra fast. So now indeed it's very fast. We also have want to have low development overhead, and easily extensible. So all these dreams come true, right? Actually, we can also dream bigger. So in the sense that we can have new solvers, new objectives. And so, for example, not only you want to care about pure wireless, but you may care about routability or timing, etc. Or let's say you want to try new accelerators, or multi-GPU, or distributed computing, or use mixed precision, that machine learning community people that play, right? So we can actually leverage that, or we can also use a DreamPlace kind of paradigm to look at other EDA problems, such as gate sizing or floor planning, and so on and so forth. All right, so that is our first case study on DreamPlace. So next, I will talk about our magical on machine-generated analog IC layout. So this is a project funded by DARPA ERI through the IDEA and POSH program, which I'm leading at the UT Austin. So we are also just actually already made the magical open source, the version 1.0. So feel free to download and try it. So let me give you a high-level view of the magical. As I just show you, right, DreamPlace essentially focus on digital IC. We're talking about tens of millions of standard cells and many, many hundreds of IP blocks, right? But analog ICs, you don't have so many transistors. Usually, you may talk about hundreds of transistors, right? But those are really, really hard to design. So that's why analog IC designers treat it kind of like black magical, or still they use manual designs. Right? It's very tedious and error-prone, in particular during the layout stage. Right? So there are so many symmetric stuff you need to consider. There's a digital flow. There are also different performance metrics. So again, right, our magical mission is to develop a fully automated analog layout systems, leverage human and machine intelligence. We have already got a lot of very exciting, promising results. Here are some of our papers, which have already been presented or to be presented. But let me give you the high-level overview of the magical layout systems. So basically, the input is a netlist, right? Like SPICE netlist with PDKs, certain technology, right? And the output is GDS2 layout, which is DRC LVS clean. And in the magical, we will also do some device generation based on the parametric instance that is given by the netlist. But the key portion here, the three key components are the layout, automatic layout constraint generation and extraction. And we will use some pattern matching or other kind of analysis techniques. And then once we generate this kind of constraint, in particular like symmetrical constraints, and also hierarchical level, not only just the block level, but also hierarchical level constraints. then we will use those constraints to guide our placement and routing engines so that it will honor those constraints. So we actually got some very exciting preliminary results. Here is just some very small test cases. It's a two-stage Miller compensated OTA designs in TSMC 40 nanometer. This actually my collaborator, Professor Nansun, he's my co-PI for this project. He actually, his group already tapped out this chip before. And so we actually, this is our magical layout. As you can see, right, magical layout is very, very different compared to the manual layout. But if you look at the electrical and the performance such as DC gain and input referred noise and CMR, etc., actually our magic is very competitive. But in terms of runtime, by the way, this is a small, relatively small circuit, but still takes a very experienced PhD student like a week, right? But in magical, it just takes seconds, right? Orders of seconds. And so then we can actually do a lot of iterations and generate many, many different layouts. So in fact, we also released some benchmarks that using magical, we can easily change different placement, net weight, and so on and so forth. So we can generate thousands or tens of thousands different layouts, and then we can do post-extraction simulation, and then which can actually help people to do machine learning, right? So anyway, so I think we are very excited about this project, and now let me move on to the third one, a case study related with machine learning AI for IC. So this is more linking like design to manufacturing. So one specific paper that I would like to cover is lithoGAN. Essentially, it is presenting an end-to-end lithography modeling using generative adversary network, right? So this is a paper we published at last year's deck. So as we all know, right, lithography simulations is extremely complicated in the sense that, okay, once you have a mask, right, it goes through your like optical and photoresist systems. So you will through the optical systems, you will have light intensity distributions. Then it will go through the etching and so on and so forth. So if you want to simulate, for example, a 2 micron by 2 micron area, like this clip, using the very advanced, S-litho, for example, from Synopsys, which has a lot of, you can imagine, a lot of physics, optics, chemistry involved, right? So it takes a minute, right? So there's no way that you can use this kind of simulators in the design loop, right? So one thing naturally people may ask is that, hey, without going through these detailed lithography simulations, can we directly predict whether you have some hotspots, right? Because hotspot is where you will have poor yield, right? So it turns out that this problem is very natural, and even more than 10 years ago, right, my group has started to use machine learning for hotspot detection of this lithography. So at that time, it's not deep learning. We just use some support vector machines, right? But later on, of course, there are many, many papers people have published along this line for lithography hotspot detection. And there's even an ICCAT contest back in 2012 run by Mental Graphics on this. And people have used, for example, you combined machine learning and pattern matching, and there's a deep neural network work proposed by Professor Beiyu's group, my former PhD. And then there's also a question like how much learning data you need, big data versus small data. So we also have done a lot of work, on transfer learning, active learning, semi-supervised learning, etc. Right? Well, this problem is relatively easy to understand in the sense that, sure, you can, take it as an image, and then it becomes a classification, hotspot yes or no, right? It's like cat or not cat. An easy binary decision problem, right? Actually, a harder question is that can we directly predict the printed images? So it's not just yes or no, hotspot or not, right? I want to, because for sometimes you do want to know the exact printed image. So to get that, we actually got inspired by the recent advancement in GAN, generative adversary network proposed by Goodfellow. So essentially, at the higher level, right, you have two networks, neural networks, right? One is called a generator. It's just keep on generating something. Then the discriminator will say, yeah, this is good, this is not good. For example, if you want to generate a fake $1, right? So bad guys keep on generating this, but please catch them, and then oops, after many iterations, the bad guy can generate some fake $1 pretty nicely, right? Kind of not expert may not tell, right? So GAN is very, very powerful, and the conditional GAN, C-GAN, is similar to GAN. It's just like it can do transform from one domain to another, right? So yeah, like here, right? So from this street you can generate, you can strip out the trees and so on and so forth, and from this black-white color you can put colors, right? So how we can do domain transformation? So essentially, to do image translation for lithography modeling, what we do is that, let's say you have your mask and you care about some image that you really want to know what is my printed image, right? So like here, right? So what you can do is that you can capture the clip, that is the area that will influence this image. And then instead of doing very detailed simulations, what we can do is that, we can directly do image translation from this, and we can get the printed image of this, like, for example, a veer that you care about, right? So instead of using expensive litho simulation, we do an image translation using C-GAN. But it's a modified, image translation, because the resolution and the image size of these are somewhat different, right? But anyway, I won't go into the details, but with this, we actually have we use detailed simulators to generate a bunch of training pairs, right? Learning data, right? So you have input pairs for, we generate thousands of these. And then we will actually, next time, we'll do this kind of training, we'll have generator network and discriminator, right? So anyway, I won't go into the details, but the question, the result is very exciting. So for example, here, right, after like 80 epochs, it actually can converge, and during the training. And once we have done the training, right, so then it is just a learning, it's just the inference stage. Give me any of this, so we can quickly get to the output. So it turns out that we found that this litho GAN, compared with the rigorous simulations with acceptable errors, when we consult with the industry, our litho GAN is like 1,800 times faster than the rigorous simulations, right? So for example, here the blue one is our image, but this red ones is from the rigorous simulations. Yeah. So as you can see, it's actually very close. And then with this printed image, then you can, if it is a transistor, you can slice them, and then you can know what is the IV characteristics and so on and so forth. Right? So not only we can get the printed image, but from any of this input mask pattern, but we can also use GAN to do SRF insertion. So this is a work we also published in last year's deck. So as we all know, right, so to print very, very small patterns like veers or contacts or wires, right? So you do need to insert a bunch of so-called super-resolution assist features, like black stuff here, which are very, very small, tiny, won't be printed in the end, but they are very important to help you to print those patterns, right? So usually, as you can see, this is a very, very computational expensive step, because you not only, you need to, for example, if you try to flip the pixels and so on and so forth, you have so many solution space to explore. And if you're also going to core very accurate lithography simulations, it will take a tremendous amount of time. So, but using our image translation, so basically from here, we can directly translate to this image and directly generate the SRF, right? So we found that compared with model-based SRF insertion, we can have hundreds of times speed up, all right? Okay, so far, I spent most of my time talking about AI for IC. So I'll use the next 10 minutes to talk about some IC for AI aspect. Basically, as we all know, IC, nowadays, right, customized IC or IC accelerators are everywhere, right? From TPU to like all the all the phones, smartphones have these neural processor units, right? But they are all based on the conventional transistors and the electronics, right? So like 2 years ago, MIT published this chip called the optical inference chip. Essentially, the idea is that they can actually use optical and nanophotonics device and integrate it with electronics to do inference. So actually, after they published this chip, there are also already a few startups, right, to look at this. Because the key idea here is that they could provide orders of magnitude to the more energy efficient, and also the throughput is much bigger. So let me show you the top level idea how you can do this kind of optical neural network processors. So what is the key idea? We know that in optical neural network and this training, one of the key computation steps is matrix multiplication, right? And to do matrix computation in digitally, of course, you have to convert them into digital, and then you combine it and you do all this computation, right, using GPU or whatever, right? But here, it's a more like an analog computing concept. It's like you can think about your light intensity can represent some vector values, right? And then, the middle part, which is your optical kind of array, device array, you can imagine this can implement some kind of matrix. So then, once the input light goes through this, optical device arrays, then the output here, the light intensity is directly the matrix vector multiplication. All right. So then you can see, wow, that is really fast. I don't have to go through any of these digital computations, directly light in, light out, right? And then it's already multiplied, matrix multiply, vector multiplication. And they also show that, at here, you can detect the light in over 100 gigahertz rate. And once you configure it, pretty much it consumes almost no power, right? And of course, the question is that you need to configure that properly. But another key limitation of optical neural processor is that the optical device, compared with the CMOS transistors, the optical device is much bigger. You are talking about the orders, like for CMOS, we are talking about the 5 nanometer or 7 nanometer, right? For opticals, you are talking about, instead of nanometer, you are talking about the micron, right? 5 nanometer or 10 nanometer microns, right? So we are talking about 1,000 times bigger, right, in terms of dimension. But I think, if you can deliver very, very low power and very, very high throughput, I think there's still a market for that. You probably also heard about the Cerebrus. They have an entire wafer is a machine learning AI chip. Right? I mean, it's not the chip; it's the entire wafer, right? So, but one of the key problems, as I just mentioned, right, area is a big concern. So one work that we have done is that compare with the original paper from MIT that was published in Nature Photonics 2017. So what they do is that they will do a software training first, then try to match those weight and do some singular value decomposition, and then for those unitary metrics, they will then implement them into those optical devices, MZI arrays, right? However, this kind of array, area is big, so you will need n divided by 2 plus n divided by 2, so in the order of n squared number of MZI components, right? However, in our architecture, at the higher level, right, we use a hardware and software co-design in the sense that, we will propose a new architecture. This new architecture will not handle any arbitrary weight, and but it will use much less number of MZIs. As you can see, it's kind of like a half of that, almost right? Because here you need n squared over 2 of them, right? Here you only need one big array. So that's why you can have a smaller area with 0 accuracy loss, but and also better noise robustness. But the question is that here we do need to have a software and hardware co-design. Okay. So here's some results that we showed that compared with the original paper, we can reduce the area by like 38%. So in this year's ASP deck, which actually we proposed yet another architecture, we call it FFT-based ONA. So for the previous one, we used MZI, but in the new architecture, we don't use MZI. We use actually directly FFT-based architecture. So we actually got the best paper award from this ASP deck. Again, we need the software and hardware kind of co-design and co-optimization paradigm in the sense that, for this new architecture, we will handle only circular matrix multiplication. So a circular matrix is like a more special matrix, and which can be easily implemented using this FFT kind of structures. It's not as general as MZI, like in the previous work, but even in the machine learning community, right? So they have shown that this circular matrix actually has very good expressiveness. And but the key advantage of this approach is that, okay, it now has much smaller area, less latency, and better energy efficiency, right? So I won't go into details, but basically, here 3 points. This is the area. This is we can get to the same accuracy, but in terms of area, compared with the original MIT paper, it is like a up to 3.7x reduction, right? So this is a different vertical bar shows, original MZI, then our ASP deck slim MZI, but then with our new architecture, we can actually reduce the area very significantly. And in terms of latency and energy efficiency, this is the original MIT's paper. And from here, we can see we can reduce it by a factor of 10, right? For both energy efficiency and the lower latency, right? And the last case study for the optical neural network is our work called FLOPS, right? This is just published at this year's Design Automation Conference. And so basically, the previous two work only does inference, right? And once you have an inference, you basically map it to certain weight, and then you train that weight, and then it stays there, right? So, but usually we also would hope that we can also use the optical neural network to do the training, right? But training in general is much harder because you have a forward propagation and backward propagation steps, right? And that's why we use the stochastic zeros order optimization, because otherwise to compute a gradient is pretty hard, challenging. But anyway, I won't go into details, but compared with some previous work, we can get a much higher efficiency, and we can also have better scalability, and so on and so forth, right? So for those of you who are interested, right, you can refer to this paper. But one thing I would like to point out is that when we are doing this kind of on-chip learning, very nicely is that it has built-in variation handling, right? Because for those optical devices, right, so usually they are kind of susceptible to the noise, like the thermal variations and so on and so forth, right? Usually, right, if you want to model the new thermal and then try to do the thermal simulation and fit it back and then try to learn again, that takes a lot of time. But because now we are doing everything on hardware, on chip, so we can directly reflect those thermal variation will be directly reflected in the physics there. So we can actually get very fast feedback and also to be much more robust, right? So for example, we show that compared with the previous model, if you just do software training and map it to software with crosstalk noise, thermal crosstalk, you may drop like a 5% or 6% drop. But using our model, right, so although maybe originally we may not be as accurate as the ideal software training, but we don't have any drop, right? So ultimately, we are actually 5% more accurate in terms of the ultimate training accuracy, right? All right, so now let me conclude. So in this talk, I kind of showed you how we can use AI to do better placement through DreamPlace, through litho gain or SRF gain, right? So meanwhile, I also showed you, Magical, our new analog IC design layout framework, which have no human in the loop. So I also showed you some case studies for, developing ultra fast, which is light speed yet ultra energy efficient optical neural networks with the photonic integrated circuits. Again, as I mentioned, the hardware and software co-design is the key. And oops, sorry, I think I skipped too fast. So using several case studies, right? We also tapped out of a chip of our FFT-ONN is currently under testing. So we are very excited about this. So to conclude, so I think for future AI and IC needs really to have a close synergy between them. On one hand, using smarter AI hardware and software, you can design better chips, and meanwhile, better chips can help you run AI algorithm faster. So as John Hennessy and David Patterson pointed out in their Turing lecture 2 years ago, really, I think now is a golden age for hardware and software co-design, and also enable us to do agile chip development. So that also, is my thing for this talk. So I like to acknowledge different funding agencies and collaborators, and of course my students and postdocs who do the real works. Thanks very much, and that concludes my talk. I'll be more than happy to take any questions. Okay.
So thank you very much, David, for this very nice talk. So we are open for questions. You can do your questions by the YouTube chat channel, and the ones that are logged in the MConf also by the chat channel of MConf. So I have one question that first, congratulations for your work on the physical design automation of analog circuits with Magical.
Yeah, thank you.
Okay. Yeah, one question related is it's in reality it's one tool, or it's a set of tools dedicated to different types of analog circuits? How you manage all these different complexity of each analog type of circuit?
Yeah, at this time, right, we have tested on different circuits like OTAs, and we also even tested for the entire ADC, right, Delta Sigma ADCs. Of course, at this time, probably we cannot handle all kinds of analog, but we'll be more than happy to try them out, right? So once we try more circuits and more people try them, we'll see where to improve, right? So, but currently the tool is all packaged together. So essentially, we have constraint generation, device generation, constraint generation, placement, and routing all integrated together. Right?
Thank you, Dave. So I have here a question of Professor François Rivet from Bordeaux, France, that attend your talk. So he works in RF circuits, and so thank you, François, for your questions. So his question is, when my job as IC designer will be part of good memories, will it disappear rapidly?
Okay, so first of all, don't worry about the jobs in terms of, we are not trying to replace IC designers, right? As a layout tool here, right, we are trying to make your job easier, right? So although we say that it can be fully automated, right? So we actually can also take, in this tool, we can also take a designer input, right? So for example, if some designer says, hey, this tool needs to be symmetric or need to satisfy certain signal flow and stuff like that, we'll be more than happy to do it, right? So also, even when DARPA says in their initial statement, right, they have no human in the loop, 24-hour turnaround time, right? So they also have a little bit of disclaimer there. So okay, maybe 2 times PPA is okay. So basically, right, if we are doing this kind of thing, so compare with like you through hundreds of engineers, tune everything, and so probably we, of course, you can use our tool as a help, and meanwhile, if you still can afford more human involvement, right? So our tool's goal is to really make the tedious part, and also can, if some companies, so they don't have that many designers and they don't care about the PPA that much, they can say, hey, allow 2 times PPA or some kind of degradation. I'm still okay. I'm cool, right? So I think in that case, it's still okay, right? And also with this, probably it can also help designers to, we can now have more kind of designs, right? That's why I think in one of my slides, I was saying we can democratizing IC design, right? So previously, IC design, the bar is very high. It's not like software designers. You write some code, you compile it down, right? But the hardware compilation is like non-trivial at all. So using our tools, maybe more people can become hardware designers as well. And then everyone maybe also through the cloud or through some very cheap manufacturing. So you can, many more chips can be designed. Then we also need more circuit designers. Right? So I hope, I don't think it is the goal is to replace hardware IC designers. Right? It's just like your innovation maybe a little bit different place. Right? I hope that answers your question.
Okay, thank you, David. So I have a question by Professor José Luiz Gintzel from Federal University of Santa Catarina at Florianópolis. So he says, hello, David. Thanks for the excellent talk. In your opinion, which is the physical design step that can take most advantage of machine learning techniques?
Well, I think as I already showed you, right? So in the physical design, right? Like DreamPlace certainly take a lot of advantage, but the DreamPlace actually doesn't need training data, right? Because we are essentially using the hardcore training engine inside those neural network training to solve the placement problem, right? So we kind of tweaked it a little bit, right? But in terms of a lot of training data, I think mask synthesis, hotspot detection, those areas, or even mask synthesis, like lithography, kind of quick model, right? That kind of areas can certainly, if you have a lot of, you can, on one hand, you have a really accurate physics-based simulators. You got a lot of, training, like test the training data, right? Then you can learn it, right? I think those areas can certainly help a lot, right? For analog designers, for analog designs, right, we also try to use a lot of, design experience that from our design communities, right? So then to train some of the, for example, the routing guidance, or also another thing, right? For example, okay, let me also even go back a little bit, right? So as I mentioned, right? So machine learning essentially can act as both hammers and bridges, right? So for as long as any place that you can improve each step or try to build bridges between the steps, I think that's where machine learning can help greatly.
Thank you. I have another question related to the medical. So how you can handle the tool or adapt the tool to different technologies, for example, bulk CMOS, FD-SOI, FinFET.
That's a huge development, right? That's non-trivial, right? Because ultimately, let's say, sure, at a higher level, maybe you can do something. Placement, global placement is also okay, but ultimately, if we want to have a GTS2 and which are DRC clean, you have to handle technologies, right? So that's why in EDA companies, right, when they migrate from one technology to the next and so on and so forth, that's through a lot of engineers, right? So we only have a small team at the university, right? So at this time, right, we have tested our tool can work for TSMC 40 nanometer, right? So we already have tap out, which is silicon proven, right, for our magical layout for some chips. But if we want to have other technologies, like I think, of course, we have to change our router or placer a little bit, right, to satisfy those DRCs. Right? But I think the bulk part should be similar. One hand, right? So on the other hand, right, if you are changing from bulk to FinFET, that's definitely a lot of tool migration things to be done, right? Okay. Recently, by the way, Google also worked with Skywater. They said they're going to release the free open source PDK, which is can be manufactured, right? So they may, if you have good chips that may be tapped out using 130 nanometer Skywater, and you apply for Google's shuttle, so they can even free type out, right? So we are also looking to work with them, right? So, but anyway, so this is definitely right to supporting different PDK stuff like that. Takes effort.
Okay, thank you. So I have a question by Vinicius Calegaro from Mentor Graphics in California. So AI transformations are hard to understand in the context of optimization systems. Was there any wow moment during the experiments that lead to a new systematic algorithm instead of an AI-based one?
Sorry, I'm not sure about that I understand the question. So he's talking about the entire AI systems and layout systems. Is a more philosophical question, or can you repeat it?
I think it's more a general question, but you have also a copy of the question in the
the window, right? Okay, let me see.
I can repeat. AI transformations are hard to
okay,
understand.
I got it. I can see it now. Right,
Yeah.
Okay. Okay, so yeah, I think AI is just one kind of tool, right? I mean, if you can solve it analytically, right? Like even in our, for example, DreamPlace or even in our Magical, right? So we didn't say, oh, you just use AI, right? So if there's a well-formulated mathematical problem, for example, even in the placement, right, we have well-formulated placement problems that can be, it's a systematic optimization problem, right? But we just leverage the AI kind of hardware and software to solve it, right? In this situation, right? But in terms of the optimization engine itself, right, it is actually optimization problem, right? Okay.
Okay, I have a question by Professor Abe.
Oh, okay. I can see the question now, right? Oh, thanks.
Yes.
Oh, maybe you want to repeat the question for the audience?
Yes, I have to repeat the question for the audience. Nice talk, David. So before that, Fadel is from Abu Dhabi, so United Arab Emirates. No? So thank you for the question, Abe. So he's saying, nice talk, David. Also very nice results about using machine learning for physical design. Any similar results for logic design and high-level synthesis?
Okay, so first of all, hi, Ed. Yeah, really nice hearing from you. Yeah, my main research area is more in the physical design for manufacturing, right? So we also have some results in logic synthesis. For higher up, I'm sure there are some results, right? From, for example, Professor Demin Chen's group, Professor Zhiru Zhang. I mean, many people are also working in that community, right? They also try to take advantage of the newest machine learning to solve that problem, right? But I'm not expert in that area, so, but I'm sure there are works there.
Okay.
Thank you.
Vinicio is just clarifying the point about his question. So he's saying that, yes, it's a philosophical one, in the way sometimes we don't completely understand why the AI is taking a specific decision.
Okay. So that's definitely one of the hardest challenge for, in particular, is the neural network, deep neural network. There's the explainability, right? So why it works, right? Even in the hardcore machine learning community, right? That's one of the, I don't know, at least $1 million, maybe $1 billion question, right? So yeah, I think that's that's definitely a very, very big research topic, even in the big AI community, right? The explainability, right? And why AI can take certain specific decisions. Yeah.
Okay, thanks. So we have now a question by Victor Costa. Thank you for the great talk. Do you believe that photonic ICs will ever reach the small area of current CMOS ICs?
Okay, so by the way, I have to say that I'm not an expert in nanophotonics. For the nanophotonic project, I indeed work with device guys, Like at the UT Austin, we have a Murray Center led by Professor Ray Chen, and he's a more optical device guy. But in general, right, the optical device is much bigger because of some light. There's some physics there, right? So it's just different to compare with the CMOS transistor, right? So that's why you cannot. You probably can scale, right? But may not be as small as CMOS, right? I mean, of course, you know, who knows, right? Maybe some really revolutionary stuff may come out in the nanophotonics community, but for the time being, yeah, I think it's still way to go, right, to reach the CMOS kind of nanometer scale. Right?
Okay. So just by the way, Victor, that has done the question, he is from Federal University of Santa Maria, but now he is in Sergipe, in the northeast of Brazil.
Oh. Okay. Nice.
So I think I have no more questions. So it was also great to have, as you were able to see, questions from many locations in the world. No?
Yeah, also some questions from people I haven't talked for a while, right? Really nice attending my talk, right, through the YouTube. Right?
Yeah, we have
organizing this.
Yeah, from the people that put their names and the locations in the chat of YouTube, we have people attending from France, Ireland, Poland, several ones in USA, in England, in United Arab Emirates, and many locations in Brazil. So thank you very much again, David, for this excellent talk. And I hope to see, well, there is another question here from Miguel Cafruni.
Oh, okay.
Talking about FPGA for planning, AI for AC dispense with placing P blocks manually to obtain the lowest possible Y lengths in whole design?
Okay, so this question is related with FPGA floor planning or placement, right? So my group indeed work a lot on the FPGA placement as well. But I mean, in some portion of the FPGA placement, we have used some AI. For example, you know, we published a paper at this year's SPDAC to do like a routability prediction of FPGA placement during the FPGA placement, and then to feed it back to the FPGA placement. I think if you are talking about the general FPGA floor planning or higher level floor planning placement, I mean, so maybe you can also use some reinforcement learning, like Google recently have done for the macro placement for ASICs, right? We haven't done that yet, right? But also for FPGA placement, again, right, it can be formulated into some analytical optimization problem. So for example, we have actually one of the state-of-the-art academic FPGA placement called ELF-Place. I can put it in the chat box, ELF-Place, right? So that is also, again, using analytical engine, right? Because analytical engine in general can give you very high quality result, also fast, right?
I have here Professor José Luiz Guinso from Federal University of Santa Catarina. He's saying, we would like to count on Professor David Pan talk in the next IEEE season school on physical design automation that will take place in 2021 in Florianópolis, Brazil. So it was scheduled to be this year, but as you know, in function of COVID, it was transferred for the middle of next year. And he also saying that this is an invitation. So we all hope to have the participation of Professor David Pan in person. So I hope that this will be possible. So
oh yeah, I will be more than happy, right? I have visited Brazil a few times, but not yet to Florianópolis, right? So it's a beautiful city, right? So yeah, I definitely look forward.
Wonderful location with very nice beaches.
Yeah,
with a lot of shrimps, oysters, and they have a very good experience or demonstration of technology transfer from university to the society. They brought some oyster from Chile, and they managed to help the local fishermen to produce oysters. And the result is that the oysters in south of the island are twice bigger than the original ones that come from Chile. Yes. So,
nice.
And a very nice university with also a very nice group of microelectronics in the computer science department and electrical engineering department. So it will be a great event. And I hope that all this COVID problem will be finished till there.
Yeah, yeah. I look forward to that.
Yeah.
Definitely.
So thank you very much again, Professor David.
Okay,
for
thank
this,
you very much.
Excellent
Really
talk.